Alrighty, so let's do some chapter 14 without any further ado. So the rules for aromaticity, we covered this last time, so I don't want to erase and rewrite, but we can go through it step by step. So there's 3 different categories for aromatic systems, right? We have aromatic, non-aromatic, and anti-aromatic. And when we're talking about order of stability, aromatic is super stable. We love it. Non-aromatic is just like chilling. It's whatever. And then anti-aromatic sucks. It sucks so bad. We don't want to be anti-aromatic if we can do anything about it. I also want you to know that aromatic is a lot more stable than conjugated. So if we have benzene versus this guy, right? They both have 3 double bonds in conjugation. They're both, whatchamacallit, 6 members, right? But the aromatic ring is so much more stable. All right, now that we got that out of the way, the rules to be aromatic are very kind of particular. So first of all, it has to be cyclic. So everything in chapter 14, everything that's aromatic has to be a ring. And it has to be planar. So planar is one of those things that a lot of students, including myself, have trouble seeing. So we're going to say that anything smaller than an 8-membered ring, and this is what an 8-membered ring looks like, anything smaller than that, we're going to assume is planar. Once we get to rings that are more than 8 members, that's when we kind of have to look at it and decide, is this planar or not? And then we have fully conjugated. So in order to be considered fully conjugated, every atom has to be sp2. So we cannot have any sp3 in there. And then last but not least, we have Huckel's rule, which is 4n plus 2 pi electrons. This is one of those ones that students look at. Sorry, I read the name Taylor while I said that. Students will look at this and they'll be like, what the heck? Like, I have no idea what this is trying to tell me. And I totally get it, because people are like, all right, well, what do we substitute for n? Like, what does this mean? The reality is, you could substitute any real number for n, and it's not like an equation that for each one you have to like do the equation and figure out how many electrons it has to be. It's more so like, if you have any of these numbers present, it's going to be aromatic. So what I suggest is don't spend too much time with the 4n versus 4n plus 2 rules. Just know that 2, 6, 10, 14, 18, those are all going to be aromatic. But if you have anything that is just a multiple of 4, those are going to be anti-aromatic. So something you should be aware of, anti-aromatic and aromatic are very similar. So to be anti-aromatic, you have to follow the first 3 rules, which is cyclic, planar, fully conjugated. The only difference, like I said, is instead of 4n plus 2 electrons, we just have a multiple of 4. So 4, 8, 12, 16, so on and so forth. And then non-aromatic is just breaking any of these rules. So if you have an odd number of electrons present, so like an odd number of radicals, or if you have any number besides either of these rules, it's going to be non-aromatic. If you have any sp3 atoms, automatically non-aromatic. If you have anything non-planar, automatically non-aromatic. So non-aromatic tends to be like the easiest one because it's just breaking any rules, but it's also one that kind of slips through the cracks. So any questions thus far about the rules? Cool. And then if you want to screenshot this or whatever, that's totally chill with me. These rules are super important. All right, so let's go to these examples. Before we start the examples, someone had a question earlier, which was a really great question, and it was, how do we know sp2 versus sp3? So sp2, the only things that will be sp2 are double bonds, anions, cations, and radicals. Those are the only sp2s. If we have a carbon, such as this one, that has 4 happy little single bonds, that is sp3. And right off the bat, if we have sp3, this is what? Aromatic, anti-aromatic, or non-aromatic? Non-aromatic. Agreed. And then you can either like shorten these as A, Na, or AA, or you could just say A and then non and then anti, whatever makes you happy. All right, so that one was easy. We saw sp3, you immediately kick it out. What if they are cyclic, planar, and fully conjugated, right? How do we tell the pi electrons and whatnot? Well, what I want you to do, just in the beginning, you don't have to do this for every single one all the time, but you're just going to draw your p orbitals on each carbon, right? Plus charge means that it's empty, and then every one that's part of a double bond has 1 electron. So how many total electrons do we see in this? So each double bond is going to be 2, and then we have 0 here. So it's actually going to be 2 pi electrons. So each of the carbons that's attached to a double bond has 1, and then this one is empty. So we have 2. And so 2, is that under aromatic or is that under anti-aromatic? What do we think? Aromatic. Yes, I agree. So let's do another one and look at the counting, because I know that's hard at first. So ugly. All right, now we have a negative charge. And negative charge means we have 2 electrons. And it's occurring to me that you can't really see these electrons because they're the same color. So there's 2, 1, 1. So in total, how many electrons do we have? Yes, now we have 4 pi electrons. So if it's 4, does that follow aromatic or anti-aromatic? Okay, we got 1 vote for aromatic, 1 vote for anti, and I am going to say it's anti, because remember, aromatic is 4n plus 2, so that's going to be 2, 6, 10, 4, 12, 14, 18, etc. And then anti-aromatic is going to be multiples of 4, so it'll be 4n, so 4, 8, 12, 16, etc. I don't know what keeps changing, but something keeps changing on the screen, and it's driving me crazy because I don't know what it is, but it's fine. All right, so in the next one, we have a heteroatom. So let's take a quick look down here at our heteroatom rules. All right, so we were going through them in the last tutoring session. They're not all written down yet. But the first thing that we were looking at is single bonded heteroatoms donate up to one lone pair of electrons, and they get to choose between sp2 or sp3. So again, single bonded heteroatoms can donate up to one lone pair of electrons, and they can choose to be either sp2 or sp3. Boron is the exception, but we'll talk about that in a second. So let's go up here. Let's look at this guy. It has a heteroatom. It's single bonded. So the first part of that was it can only donate up to one lone pair. So if he shows you an oxygen with two lone pairs, you're just going to get rid of one of them. That's just there to trick you. Okay, now we're going to decide between sp2 versus sp3. So if it's sp3, it has to automatically be what? Non-aromatic. Perfect. So anytime we have sp3 as an answer, it's always going to be non-aromatic. And someone said anti-aromatic. Remember, to be anti, it has to follow the exact same rules, 1 through 3. So it has to be cyclic, planar, or fully conjugated. So sp3 would break the fully conjugated rule. So anytime we have sp3, it has to be non-aromatic. Okay, if it was sp2, now we have to think about counting the electrons, right? So if it's sp2, it has to count both of these electrons. So it has to count one whole lone pair. So we would have 1, 2, 3, 4. So it would be 4 pi electrons. Is this going to be aromatic or anti-aromatic if it's 4 pi electrons? Hint, you can look up here. Yeah, exactly. So if we have an sp3, it can never be anti-aromatic. Correct. But in this case, if it chose to be sp2, it would be anti-aromatic. So now the oxygen can make a choice. It could either be sp2 and be anti-aromatic, or it can be sp3 and be non-aromatic. Which one of those, excuse me, I had a hiccup. Which one of those sounds more stable? Okay, let's run really quick up here. So I'm going to stress this really hard because this is super important in this chapter. Aromatic is wonderful. We love aromatic, top tier, super stable, awesome. Anti-aromatic is awful. Anti-aromatic is the worst. We do not want anti-aromatic. Every ring is doing everything it possibly can to not be anti-aromatic, because anti-aromatic is awful. And then non-aromatic is whatever, it's meh. So we, if possible, we want to be aromatic. If there's a choice between aromatic and the other two, we always want to be aromatic. If it's a choice between non-aromatic and anti-aromatic, we're going to choose non-aromatic because anti-aromatic sucks. We want to be aromatic, but if it's a choice between just those two, we want to do anything we can to not be anti-aromatic. So, if I give you something like this, and you have the option between being sp2 and being anti-aromatic, or being sp3 and being non-aromatic, what do you think the molecule will choose? Non-aromatic. Yes, I definitely agree. Sorry if that was like a little bit aggressive, but this has to be pounded into people's heads. So this sucks. So if we're given the choice, we want to do sp3, we want to do non-aromatic. So this oxygen is sp3 hybridized. And our answer is going to be non-aromatic. Any questions here? Okay, let's do another example. This one. Not that one, this one. So we have nitrogen, and this time, instead of showing you 2 lone pairs to trick you, he shows you 0. But we know that nitrogen has 1 lone pair of electrons, and we also know that nitrogen is a heteroatom, and since it's single bonded, we can choose sp2 or sp3. So if we choose sp3, it automatically becomes what? Yes. I think you guys said it. It's going to be non-aromatic. And then if it's sp2, how many electrons is the nitrogen going to donate? And then I can repeat that question. So the question was, if it's sp2, how many electrons is nitrogen going to donate? So how many of those are going to count towards our pi electrons? Do you want to count it together? We can do that. Okay. So we're going to have 1 here, 1 here, 1 here, here, and then 2 from the nitrogen. So with heteroatoms, it's all or nothing, right? So it's either sp3 and it's donating 0 electrons, or it's sp2 and it's donating 1 whole lone pair, and that would be 2 single electrons in that lone pair, right? So we would have 2, 4, 6 pi electrons. Cool. So 6 pi electrons, which rule does that follow? Aromatic or anti-aromatic? Aromatic. Cool. So which one of these 2 would we want to choose? Yes, we would want to choose aromatic. So unlike the example we just did, we're going to choose to be aromatic because that's much more stable than non-aromatic. So that will be sp2 hybridized and donates 1 lone pair. Any questions? No. Okay, cool. So the kind of asterisk that you have to put into that rule is boron. So boron is kind of annoying, and it is going to be like an exception. That's the word I was looking for. It's an exception to the rule. So even though it is a heteroatom, right? Because of its position on the periodic table, it's always going to be sp2, and it's going to donate 0 electrons. So it's almost like just replacing it with a carbocation. So let's do an example. Here we have boron. And as we said, boron has to be sp2. So I'm going to write must be sp2. And it has 0 pi electrons. So we're going to say it's cyclic, planar, and fully conjugated because it is sp2. But how many total pi electrons do we have if it's only the double bond? And then there were 2. What do you guys think? How many pi electrons do we have total? 2. Awesome. So it's 2 pi electrons. It doesn't get to choose, but it is going to be aromatic. Yay. All right. So the next rule is with double bonded heteroatoms. So this has 2 different types. So it could either be double bonded inside the ring or outside the ring. So if it's double bonded, inside the ring, it's going to be sp2 and only donate 1 single pi electron. Versus if it's outside the ring, it's going to be sp2 and it's going to donate 0 pi electrons. So let's look at the difference between these 2 kind of examples. So right here, this is an example of double bonded outside the ring. So we can almost just consider this as a carbocation because this is sp2 and donates 0 pi electrons. So it's going to be the same as a carbocation or boron. So cyclic, planar, fully conjugated, 2 pi electrons. So this is aromatic. Any questions on how I did that last one? Because it was pretty fast. Cool. Yay. What's the other one I wanted to do? There we go. So what if it's double bonded inside the ring? So that's going to be a little bit different. And I'm going to draw it out sideways-ish just to show you. And I know Dustin. Dang it, I almost called you Dylan again. You just saw this a little bit ago, but wow, this is ugly. Bam, bam. This is how it looks, right? So if I draw my p orbitals, I know that each double bond means I have 1 electron here. So what you have to notice is this nitrogen has a lone pair, but that lone pair is completely on a whole different plane. So the p orbital that's interacting with the rest of the molecule is the one that's part of the double bond. So this nitrogen might as well be a carbon because it's forced to be sp2 and it's only donating that one electron in the double bond. So this would be cyclic, planar, fully conjugated, and it would have 1, 2, 3, 4 pi electrons. So that would be what? Would that be aromatic or anti-aromatic? Anti-aromatic, cool. Awesome. All right, so we did both of those rules. Cool. We did the boron rule. All right, so here's another rule. Another rule is if you have multiple heteroatoms. So if you have multiple heteroatoms and they're all single bonded, they must have the same hybridization. So if you have multiple heteroatoms and they're all single bonded, they all must have the same hybridization. So let's go up here and let's find a good example. Here we go. So we have two oxygens, right? And they're either both going to be sp2 or they're both going to be sp3. If they're sp3, it automatically has to be what? sp3 is always what? Non-aromatic. Cool. All right, so if it's sp2, we're going to have to count the electrons, right? And if it's sp2, how many electrons total can each oxygen possibly donate? So if it's sp2, how many electrons total can each oxygen donate? What do we think? I'll zoom out so you can see the other examples that we did. Okay, so all right, so let's talk about it. So each oxygen can only donate a maximum of one lone pair, right? So we're going to get rid of this, get rid of this. And so at a maximum, this is going to donate 2 electrons. And remember, we said it's all or nothing, right? So it's if it's sp3, it donates 0. If it's sp2, each one donates 2 electrons. So I'll just write that down. 2 electrons each. And as a total, we would get 2, 4, 5, 6, 7, 8. So if we have 8 pi electrons total, is that following aromatic rule or the anti-aromatic rule? Anti. Exactly. So between these two, which one do we want to pick? Oh, cool. I didn't see that you responded. My bad. Yeah, sp3 and non-aromatic. That's going to be a lot more stable than anti, so we're going to go with that. No, I'm sorry. It like didn't refresh the chat for a second, and I was like, okay, waiting, and we're waiting. Okay, so we have another example of two oxygens, but well, two heteroatoms, but we'll talk about that in a minute. So the other rule, if you have multiple heteroatoms and they're not all single bonded, so let's say we have one double bonded plus one single bonded. The double bonded one must be sp2 and donate one single electron. And the single bonded one can choose. And the tricky looking ones in the bottom, that has to do with like the planar rule. So we can talk about that after the heteroatom. I just want to give you the last two heteroatom rules. Okay, so if you have multiple heteroatoms and one of them is double bonded, one of them is single bonded, the double bonded one has to be sp2 and donate one single electron. And then the single bond is able to choose. So just like we did before. So for example, let's say we do this one. So the nitrogen must be sp2. The oxygen can choose, and we know that it can donate up to one lone pair. So if it's sp2 versus if it's sp3, sp3, you guys have told me a dozen times, has to be non-aromatic. sp2, for that one, we have to count the electrons. So here we have a carbocation, so it's empty. So we have one electron, two electrons, 3, 4, 5, 6. And that would actually be aromatic. So between these two, which one do you think is more stable? Also, bye-bye, Dustin. You're very welcome. Have a good evening. All right, so which one of these do we think is more stable? sp2, exactly. So sp2, aromatic, that one is going to be the winner. Oopsie. Ta-da! So I'll zoom out so you can see all the ones we've done so far. And let me know if you have any questions. Let's do a couple.
And how, like, well, yeah. I guess, how would you do, like, when it's, like, a double benzene ring? Or, like, one with,
Great
like,
question.
an S in it, too?
Okay, yeah, so sulfur is going to be exactly the same as nitrogen or oxygen. So I can put that here. That's going to count for oxygen, nitrogen, sulfur, fluorine.
Okay.
Okay. So if we have something like this, the double benzene looking thing, there's no heteroatoms or anything, so cool. We're just going to see if it's cyclic, check. Planar, check. Fully conjugated, check. So let's look at the number of double bonds. So we're 1, 2, 3, 4, 5. And that is 10 pi electrons. So does that follow the aromatic or the anti-aromatic rule?
That would be the aromatic.
Yep. Ta-da! And then what if you had something that was like a big ugly ring like this, right? So this is one of those that are 8 members. So this is when we have to start thinking about, is it planar or not? So we could, excuse me, that was a hiccup. We could do it just like we did for oxygen. So we're going to say planar versus non-planar. If it's non-planar, it's always going to be non-aromatic. If it's planar, then we have to take the number of electrons into consideration. So we have 2, 4, 6, 8 pi electrons. That is going to be which one? Aromatic or anti-aromatic?
8 would be anti-aromatic.
Yep. So is it more stable for this one to stay planar and be anti-aromatic, or for it to bend out of the plane and be non-aromatic?
Non-aromatic.
Yep. So the winner here is non-planar and non-aromatic.
Okay, and a dumb question, but what does it mean to be planar? Because isn't that like symmetry?
Yeah, that's not a dumb question at all. So all it means to be planar is that it's like just, there's no 3D shape to it. It's all just flat. And so the only reason a big ring like this, like we even have to talk about planar or non-planar, is because 8 or more membered rings have a lot of steric hindrance. So it doesn't want to stay flat because all of those bonds, like all those angles between the bonds are like super, super strained. So it wants to instead like go like this to be like a boat structure. If you keep it flat, that's what we mean by planar. If it bends out of the plane and becomes like a boat kind of thing, that's what we call non-planar for these kind of reactions. For these kind of molecules, I should say.
So like the Diels alder or whatever, those would be like planar molecules technically, or whatever reactions, whatever they would be called.
So not necessarily. Like, remember when we did the bicyclic ones that had like wedges and dashes and everything?
Mm-hmm.
So those wouldn't be planar. But if it was just one of like the regular ones that didn't have any stereochemistry or anything on it, those would be planar. So
Okay.
what we can kind of think of it as is no, I don't like that. It would look kind of like this.
Okay, so like chair conformations are planar, are non-planar.
Yes, so the chair conformations would be non-planar. So that's how this guy would look if it was non-planar. But if it was planar, it would just be flat like a piece of paper. So that's kind of the difference. And that's not a stupid question at all. I don't know if I already said that or not. But okay, so let's do another 8-membered ring. But now it has these groups. So what can we compare this to that we said earlier? If you don't remember, that's okay. I'll give you a hint.
No.
They are similar to carbocations. because it's sp2
I
and
was thinking of that word.
that's what I figured. I knew you knew it, but it was like sometimes the words are difficult. So what I always like to do is I just cancel that and I just put a carbocation. Just because it's easier to think about a carbocation, like you know it's empty, versus the ketone, you're like, what is that? Right? So this is cyclic, fully conjugated, and there are 2, 4, 6 pi electrons. So if it stays planar, would it be aromatic or anti-aromatic?
It would be aromatic.
Cool. And then we know that if it's non-planar, it has to be what?
Non-planar would be non-aromatic.
Perfect.
No. Yes.
No.
Okay.
Perfect. So then which one of these is more stable?
Aromatic.
Yep. So this one would actually choose to be planar, so it would stick flat on the page because that would give it aromaticity. So
Okay.
how do we feel about that one?
That one makes sense.
Cool. Good. Okay. So any questions at all on the ones we've done?
No.
Yay!